Okay, welcome to Lecture 19. We're going to talk about hydrologic processes. This begins the long section that will take us to the end of the course on hydrology. And so we need to kind of set the framework, kind of go a little bit over some of the basics of hydrology, the water cycle, or the hydrologic cycle, and some things about data manipulation for stream gauges as well in terms of flow duration and percentiles. Okay, so as I mentioned, we're going to talk about the introduction to hydrologic processes, and we'll talk about the hydrologic budget, atmospheric and ocean circulation, and the hydrologic cycle. We'll also talk about a little overview of precipitation, evaporation, infiltration, and then runoff and stream gauges. All these things will be talked about in more detail in later lectures. I encourage you to look at over the next 2 or 3 slides. There's various websites I've set up that kind of give you a little insight into various hydrologic processes. They're very simplistic, but they're easy to follow. And if you have a chance, I'd encourage you to look at these websites and see what they have to say about various aspects of hydrology. Speaking of the hydrologic cycle, the sun and gravity are the 2 big factors in the hydrologic cycle, and the sun basically is the engine that will cause evaporation and to have the moisture rise off the land surface, off of the oceans, the water bodies, and that process, as it rises, various processes occur. You get cloud formation, you get basically a buildup of the moisture to the point that you get precipitation back on the land. So most of you have seen the discussion of the hydrologic cycle. I'm not going to go into it in great detail, just to mention the aspects of precipitation and evaporation that you've already seen. We have to worry about evaporation off the land and interception as water gets it's caught up in potholes and leaves and the various kinds of ground cover that we have to be able to, as we're going to model this or understand the process, we have to take that into account. And then we have transpiration, which is basically the uptake of the moisture from the plants, and it transpires that moisture back up into the atmosphere. And typically, in what we deal with in hydrology, we will combine both the evaporation and the transpiration into one thing, and we'll call it evapotranspiration. When we talk about water soaking into the ground, we have infiltration, and that either goes to interflow, which is basically the moisture or the fluid moving through, the water moving through the system in the ground, but it doesn't go into the deep groundwater system. It more stays more toward the surface. And then we have the deeper groundwater flow, and we'll talk a little bit about that. Obviously, this course we don't get into groundwater in any great detail. And this subsurface flow is what we're talking about, is below the surface of the ground, and that's the interflow in the deep groundwater. Then we have surface runoff, which is the process of the rain falling on the ground, and what doesn't get infiltrated will run off. And then we have spring flow and seepage. You know, many of you from Missouri, you know that we have a lot of natural springs here, and Big Spring, Merrimack Springs is one very close to us here. Those are basically where groundwater surfaces, and sometimes appreciable quantities. All right, there's a narrated, again, another website that talks about the global hydrologic cycle, and you can visit that at the following website. All right, what is a hydrologic system? It's a structure or volume in space surrounded by a boundary that accepts water and other inputs, operates on them internally, and produces them as outputs. So basically, we try to characterize mathematically the system of water in and water out, and there's an operating process in the middle, where you get water that goes into infiltration, or maybe it gets evaporated, maybe it gets transpired, maybe it just runs off directly. And so all those things make up the hydrologic system. If we look at the land surface and the topography, we have this thing that we call a watershed, also known as a drainage basin or a catchment, and that's all mean the same thing, which means the topographic area that collects and discharges surface stream flow through one outlet. So in this particular case, the outlet's down here, and we can see by the topography there that water that falls inside this dashed line here would basically run off and come out to this point here. If it falls outside this dashed line, it would not come into this particular point. So that's a watershed, also known as a drainage area or a drainage basin or a catchment. If we characterize the watersheds and streams, we've got the hierarchy of lower order to higher order basins. And we also know this thing called stream order number. And so if you've got a basin, it starts in small basins and they combine to form larger basins, and then so on and so forth. If we think of that in the stream order, if we have a discernible stream that has no other tributary inflow into it, that's called a order 1 stream, and these are high up in the watersheds. If you have two first order streams that join together, that becomes a second order stream, and you can see that I'm pointing to it here in the graphic. If I have two second order streams joining, I have a third order stream. And again, if I have a third order stream just with one first order stream joining it, that does not make a fourth order stream. I need to have two third order streams joining together to make the fourth order stream, and you can see that down here. If I look at a perspective on drainage basins, this is Friends Creek, which is a drainage basin in central Illinois near Decatur, Illinois. So this is the Friends Creek watershed, and you can see that it's delineated here. And if I look at that in context of looking at in the bigger basin that it belongs in, this is the upper Sangamon River basin. And so you can see Friends Creek is part of the Sangamon, okay, which is part of the state of Illinois. And you can see that basically that then becomes that's part of the Illinois River basin. Okay, so here's the Sangamon, and Friends Creek was up in this area. You can see how it becomes, it's a hierarchical. It basically, Friends Creek is part of a larger watershed, the Sangamon, the upper Sangamon, which is part of an even bigger watershed, which is the Illinois River Basin, which is part of an even bigger watershed, which is the upper Mississippi River Basin. And so, again, the cartoon here, or the graphs here, show that aspect of it. And as you look, you've got the upper Mississippi River Basin here, and then you show the entire Mississippi River Basin. You can see how much of the contiguous United States that it drains. All right, let's talk a moment about atmospheric circulation. It's complex by many factors. The heating differences based on latitude, so you have much more heating near the equator than you do at 30 degrees latitude. You also have rotation and spin of the earth. You also have distribution of the source of the moisture that gets evaporated. The way the oceans are situated. So, but we have some overall general patterns that we can identify. And as you look at the circulation pattern generally of the atmosphere, this is the Earth here. You can see where we have these winds that are where you get the circulation where you have air rising and then falling back again. Excuse me. And so you get these areas where you have predominant westerly winds. Then you have the trade winds that are easterlies. They come out of the east and flow to the west. You have this equatorial area here where you've got a low the winds sometimes you get stuck in areas. The old sailors, which would have the sailing ships, they would basically get stuck in areas for long periods of time where they have no wind to actually take them on the course that they want to go on. And so you could get basically a ship could be stuck for a while in the old days. The atmospheric circulation occurs in the troposphere, which is about 8 kilometers high at the poles and 16 kilometers high at the equator. And this jet stream occurs just above the troposphere. So when the airplane, if you've flown commercially, you get up around 40,000 feet. Typically, if you're flying from west to east, the pilot will try to get into that jet stream, and that can add a 150 mile an hour tailwind, and you end up they use less fuel to get you from point A to point B, and you get there a lot quicker. And so again, this is just a very general atmospheric circulation pattern. We typically get our weather in the midwestern United States that comes out of the west, and that's driven by this circulation pattern from west to east. That's not always the case. As I said, this is a general circulation pattern, and you have to take that into account. But this is how moisture in the atmosphere moves around predominantly as we look at what is our weather generating mechanisms. If you look at ocean circulation, the oceans exert great control on the global climate. It contains a lot of heat and storage. It also contains the source of the moisture that we would evaporate and cause to come down in rainfall. An example of the ocean's impact on atmosphere and climate, most of you have heard about the El Nino. That's the Eastern Pacific water temperatures, and when it's warmer than usual, it's what we call an El Nino condition, and that induces certain weather patterns in the United States and elsewhere in the world. And so we can see that typically the El Nino pattern for us in the Midwest is that when we're in an El Nino situation, we typically have much wetter, and you can see that we're in these 8 to 9 wettest periods climatically in these various climatic regions. Have had significant wetter periods during El Nino cycles than when we are in a non-El Nino cycle. Typically, this graph right now is such that I typically download what the current El Nino situation is, what's the water temperatures. But with the federal government shutdown, you can see that we don't really have any information. What I'll do is I'm going to get rid of this for a second and pop up the real slide. And whoop, that wasn't good. Let's pop through these real quick here. Get to that slide. So this would be last year, last semester in the spring of 2013. This was basically where we were at with the temperature pattern, and this tells you what the anomalous behavior at that time was. And we were in a kind of a neutral cycle. We're around zero in terms of the departure from the long-term mean. So we weren't really warmer than normal, or we weren't cooler than normal, which is a La Nina pattern if we're cooler than normal. This is basically looking at patterns. This is the temperature in degrees Celsius, and this is the departures from normal, and this is through time. This is from 1986 down to present, and you can see when we had periods when we had warmer than usual. These are the El Nino types of periods. 1995, 96, 1993. These are periods when you have warmer than normal patterns, and where you have more runoff than you typically would, or more rain, at least in the United States. In central United States is typically attributed to when we have the El Nino pattern. We get a wetter cycle in the upper Mississippi River Basin, for instance. All right, so if we talk about generation of runoff, we're talking about from rain flowing over across the hill slopes into the receiving waters. And so this is a picture from my farm during a runoff event a couple years ago, where we had tremendous amounts of rainfall, a couple inches in about a half an hour time period. And you can see these aren't creeks up here. This is just little depression areas where the water kind of congregates and goes down. It's flowing down into my lake, and you can actually see how wet it is. And so that's the runoff mechanism. And if you were to put a stream gauge down here right before it gets to my lake, this is what it might look like, where you've got the flow rate in cubic meters per second in this case, or cubic feet per second if we were in English units. You have the rainfall that generates it, and this is the runoff that results. And so you can see through time, this is called a discharge hydrograph. All right, basically for stream gauges, we've got, we're going to learn more about that in a lab session and in a subsequent lecture. But the U.S. Geological Survey operates stream gauges across the country. And this is kind of a cartoon of what a stream gauge looks like, where it's measuring the water surface elevation in 24 hours a day, 7 days a week, maybe 5-minute increments, maybe 15-minute. If it's a big stream, maybe it's every hour. And it would be able to shoot that through telemetry. In this case, it's got a satellite antenna. Would be up where we could shoot it into the office, and then that would come out on the web. but we're really not just wondering water surface elevation. We want to be able to translate that into flow rate, volumetric flow rate. And so we have the mechanism or a model that usually in most of these gauges that you'd have what's called a rating curve, which would relate the stage or the elevation of the water surface to a volumetric flow rate. And these are real measurements here in red, and the blue is a line that basically is a best fit of those red points. And if we out here are sensing stage, which is fairly easy to do. In this case, we've got a float and a counterweight, and this is hydraulically connected to the stream. And as the river rises, the water in the pipe rises here. And so you've got the stage increases and decreases with that particular sensor. And so we have to go out and make flow measurements because we can't have a person there all the time. We make them throughout time and at various stages, and we come up with a rating curve. And from that rating curve, we know what the stage is. We use the rating curve to get the discharge. And so this is how we disseminate that. So this is basically the flow rate. And you can see measurements have been made here. And we can actually translate out on the web in real time what the flow rate, flow hydrograph is. All right. Another point, so that was about stream gauges, and we're going to talk more in depth later on. But one of the things we want to talk about is flow duration analysis. And a flow duration curve represents the relationship between the magnitude and frequency of daily, weekly, monthly, or some other time interval of stream flow for a particular river basin, providing an estimate of the percentage of time a given stream flow was equal or exceeded over a historical period. Wow, that's a mouthful. So that's a definition. Let's talk about exactly what that is. This is data that was been collected at Salt Fork near St. Joseph, Illinois, and I can take all the data over time that's been collected there. In this case, it's a daily flow rate, and I can rank that, and I can say the probability of exceedance. And so I can look and say everything above 2 CFS has 100% probability of exceedance. You get up here around, this is log space, so this is 2,000, 3,000, 4,000, 5,000 cubic feet per second. You've got a very much smaller probability that it's exceeding. So you can kind of look in a snapshot here, and you can see what are the flows that we'd expect here. 50% of the time, we would expect that the flow rate would be equal to or less than about, let's see, that's 20, 30, 40, about 48 or so cubic feet per second. So you can, with a flow duration curve, you can understand in a snapshot what the hydrology at that particular location, in this case Salt Fork River near St. Joseph, Illinois. Now I've got steps in how to build that flow duration curve. We'd have to decide what time interval. In most cases I'm going to stick to daily, at least for this class. And so that would be the daily flow duration analysis or flow duration curve. And so I'd have to find the daily flow data for that. And that, in that particular case we might have 25, 30, 100 years of daily data. We would rank that from the largest to the smallest. That's step 3. And we would come up with a probability plot based on the fact that we would have a plotting position. So we would take our ranking, our highest value, that's I is equal to 1, and we divide it. Let's say that we had 3,000 daily values of the stream flow. We would divide by 3,000 plus 1, and that would give us 1 over 3,001, and that would be the probability that would be assigned with that particular value of flow. And so that's how we would build our flow duration curve and get essentially what we would use in order to plot the flow duration curve analysis. And so I would plot that data out, and that would we would have that would be the plot would be looking like this on the flow duration curve. Now, I want to point out that we've been dealing with exceedance probability, but we could also deal with something called percentiles, which is a value on a scale of 1 to 100 that indicates the percent of a distribution as equal to or below it. So before we were talking about exceedance probabilities, this would be non-exceedance probabilities is another way to think of it. And so when you look at a lot of our flow data on the web that the USGS puts out, we're talking about percentiles of flow and not exceedance. And so there I've contrasted one versus the other. the interesting thing is the percentile is 1 minus the percent exceedance, or the percent exceedance is 1 minus the percentile. They're reciprocal in that fashion. Here's the flow duration analysis example that I might be looking at the March monthly mean stream flows, and that's maybe from 59 to 1969. That's basically I've got 11 years worth of data there, and so I can rank them from the highest to the lowest, and the number one rank would be this value of 1962, which was 287.7 CFS. The lowest one is in 1964, which is the 57.2. So here's the raw data in the first two columns, and then over here in the last four columns, I'm actually ranking them with their year and their flow value. And then the Weibull plotting position, again, just to reiterate, is I take M is equal to the rank. So on this first one, M is equal to 1, and then I'm dividing by 11 plus 1. That's N is 11 plus 1. If I go to the second one, trying to get a plotting position there, that's going to be M is equal to 2, and then the N stays the same. It's 11. That's the number of values, total number of data points I've got, and so on and so forth, and I'd work my way through on this Weibull plotting position. And then as I plot those out, you can see that for March only, I'm able to plot those 11 data points out and come up with a smooth fit through that line that would give me a flow duration for the March monthly mean stream flow. And you can look at, this is for the daily, so this is for all the Marches, and this is what the daily values look like for the period of record. So the flow duration curve can be for any time interval that you set it up to be. What are our uses of the flow duration curve? It's assessment of current flow conditions to identify problems such as drought. So if we really don't know what the flow duration curve looks like, we can't really assess, are we higher than normal, are we lower than normal, where are we in terms of classifying hydrologically what's going on in a particular channel. I might also need to assess in-stream flow habitat needs. And so if I can understand what the hydrology of a particular stream is, I know that what the channel is capable of, or what the flow rate is capable of being, and whether or not we can sustain a particular type of aquatic ecosystem. And then I also might use it to estimate the stream flow at ungauged sites. So if I've got a flow duration curve at one location, and I know what that is right now, I can almost estimate the stream flow at other sites based on the flow duration curves at our gauge locations. All right, that ends this lecture 19, and we'll end at this point.